Hello, my name is Gal Asa, and I am a PhD student at the Technion. Today, I will present a paper using nesting to push the limits of transactional data structure libraries. This is a joint work with Hagar Meir, Guy Guetta, Idit Kedar, and Alexander Spiegelman. In this work, we make three main contributions. First, we introduce nesting into transactional data structure libraries to enhance their abilities. Second, we extend PDSL, which originally had a queue and a skip list, by adding a stack, a log, and a producer-consumer pool. Finally, we present a new benchmark, which is based on a multi-threaded network intrusion detection system. I will start with some essential background about how the TL2 algorithm works. Its principles are found in many software transactional memory systems. A shared version clock is used to track objects' modification times. Every object has its own version. Transactions keep track of read and written objects and arrange those in read and write sets respectively. At the end of a transaction, the write set is locked, and next, the read set is validated to guarantee that the transaction observed a consistent snapshot of the system. Then, the objects in the write set are updated and released. Transactional data structure libraries, PDSL, is where the ease of programming offered by transactions meet the high performance of custom-tailored concurrent data structures. PDSL relies on TL2's principles, but refines read and write sets and modifies concurrency control to best fit the semantics of every data structure. For example, the queue is accessed pessimistically and has a single lock, whereas the skip list is accessed optimistically and has one lock per node. The main contribution of this work is to extend PDSL with nesting. While transactions are convenient to program as they abstract away concurrency controls from the programmer, transactional memory is not commonly used as it struggles to scale with transaction length and contention by many threads. With nesting, we aim to give longer transactions a better chance of committing. Nesting allows to create checkpoints within a transaction by limiting the scope of abort to nested transactions when possible. This reduces the amount of wasted work upon abort and improves performance while preserving the ease of programming and the semantics of the original transaction. The main idea is as follows. The parent transaction begins and executes some user code. Upon abort, the entire transaction aborts. Then a nested transaction begins, and more user code is executed. Upon abort of a nested transaction, the read set of the parent transaction is validated. If validation succeeds, only the child aborts. And otherwise, the entire transaction does. When the child transaction completes successfully, its effects are only reflected to the parent's local state rather than to shared memory. Effects are visible to other threads only when the parent commits to preserve isolation. Now, I will show how we added support for nesting to the PDSL queue. We will review the queue operation of a child transaction. While the transaction is ongoing, a pointer traverses the queue to indicate the next node to be queued. This is done without changing the state of the shared queue until commit. As long as there are items to the queue in the shared queue, the pointer moves through it. After the shared queue is exploited, the pointer begins to traverse the parent's local queue, which consists of the nodes to be unqueued by the parent. When the parent queue is also exploited, items are dequeued from their child's queue, as there is no need to keep them any longer. The unqueue operation simply appends an item to the tail of the child's local queue. Upon commit of a child, its local queue is appended to the parent's local queue for the remainder of the transaction. This figure shows the performance of three variants of PDSL in a microbenchmark that consists of relatively long transactions containing operations on a skip list, followed by operations on the queue. We see that nesting the queue operations has a positive impact on performance and scalability, as these operations have a good chance of succeeding when retried. We also implemented a few additional data structures, all with support for nesting. The producer-consumer pool treats every slot independently, with its own lock and pessimistic concurrency control. Upon produce or consume, a node is locked until the end of the transaction or until it is released by an limiting operation within the transaction. The log and stack mix optimistic and pessimistic concurrency control. The log's reads are optimistic and the pens are pessimistic, as the log's tail is the single point of contention. For the stack, accesses are optimistic as long as more items have been pushed than popped, as in that case, the shared stack is not contended in practice. This allows transactions that modify the stack to execute concurrently and commit. Our last contribution is a new benchmark of a multi-threaded network intrusion detection system application, with a few data processing stages and multiple data structures. This benchmark simulates relatively long transactions and realistic workloads. In our benchmark, packets or fragments are captured and added into a pool. Then they are consumed from the pool and are processed atomically. A part of this processing is defragmenting packets, which is done using a map. Restored packets are further processed and results are reported using logs. Thank you for listening.